Okay, let's do an example, and you're going to need your calculators to do this. So I'm going to start off by writing out the formula and then looking at how we use this formula. So this is the understanding piece here, and this is more of just a process that you need to be familiar with. Okay, starting with x1 equals 1. So this is our first approximation for the root of this equation. And we're asked to find the third approximation, we call it x sub 3, to the root of this equation. So here we go. Our formula is this: x sub n plus 1 is equal to x sub n subtract the function at x sub n divided by the derivative at x sub n. Okay, so for n equals 1, we're looking at our first approximation. We're looking at x sub 1. So x sub 2, 1 plus 1, would equal x sub 1 minus the function at x sub 1 divided by the derivative at x sub 1. So x2 is equal to 1 minus the function at 1 over the derivative at 1. So you can see that we're going to need to know what the derivative of this function is. So f at x, of course, is equal to x cubed plus x minus 1. F prime at x is equal to 3x squared plus 1. So I'm going to write this as a formula. X sub n plus 1 is equal to x sub n minus the function at x sub n, which would be x cubed plus x minus 1 over 3x squared plus 1. Where these are the same x's, so let's just leave it like that. Okay, so then if I'm looking for x2, x2 is going to be 1 minus the function at 1, which would be 1 plus 1 minus 1. 1 cubed plus 1 minus 1, just showing you every step, all over 3 times 1 squared plus 1. So what's my x2 value? 1 subtract 1 over 4. That is 0.75. And then we're just going to reiterate that process. So x1 equals 1, x2 equals 0.75. What's x3? Well, now I'm putting this value in to this equation. x3 is equal to x2 minus the function at x2 all over f prime at x2. This is getting really tedious. Let's use our calculator to give us a hand. Okay, so here is our formula that we're going to program in. So go to your equation editor and let's program in that formula. X minus, numerator, put it in brackets, x cubed plus x minus 1, close your brackets, divided by the denominator, put it in brackets, 3x squared plus 1. Then over at your table of values, we're going to put in our first guess. If the root's 1, we get 0.75 for our x2 value. We're going to take this and put it back into the function. 0.75 goes in for our x value, and this is our new approximation to the root. So x3 then is 0.68605. And if I needed to keep on going with this, I would be putting in this number, 0.68605, and I would get my fourth approximation to the root, 0.68234. And we can keep on going. Let's put in 0.68234, and I get 0.68233. And we continue this process until it's as accurate as we need it to be. That is, I asked you only to go to the third iteration. You only needed to go to this point here. But if I asked you to give it accurate to 3 decimal places, then you have it accurate to 3 decimal places, because 682 is repeating. If you keep putting this in, if I said 4 decimal places, well, I got 4. If you had 5 decimal places, you want to go until the 3 repeats. Just a little note, if you need it more accurate than the 1, 2, 3, 4, 5 decimal places that are showing, then put your cursor here and you will see the more accurate expansion below. So the procedure is going from stage n to stage n plus 1. Is the same for all values of n, and we call the formula a recursive formula, or an iterative process. Therefore, Newton's method is particularly convenient when you have a programmable calculator or a computer. So it allows you to find solutions when you may otherwise not be able to.